In this video, we are going to look at another theorem about subsequences, and we're also going to dig a little deeper into some concepts that we ran into when we were studying Cauchy sequences. So, first thing we're going to do is prove that every bounded sequence has a convergent subsequence. That is something called the Bolzano-Weierstrauss theorem. But before we do that, we're going to look at an example of a bounded divergent sequence that has convergent subsequences. We're going to prove that every sequence has, bounded or not, has a monotone subsequence. We're then going to prove the Bolzano-Weierstrauss theorem. And we're going to introduce the definitions of limit superior and limit inferior. And these are actually concepts that we ran into when we were proving that Cauchy sequences converge. So look at the sequence, what is it? -1 to the n times n over n plus 1. This, if you look at the positive terms, they all go to 1. The negative terms all go to -1, which indicates that the sequence diverges, but it does have some convergent subsequences. If we look at all the even terms, we get the sequence 2n over 2n plus 1. That one converges to 1. If we look at all the odd ones, that gives us the sequence negative 2n plus 1 over 2n plus 2, which converges to -1. So even though the sequence itself does not converge, it does have at least 2 convergent subsequences. And in fact, it has more. The question you might ask is, do all bounded sequences have at least 1 convergent subsequence? So let xn be a bounded sequence. How would we try to find a convergent subsequence? Well, one way of finding a convergent any kind of sequence, and this is especially true if you don't know what the actual limit is, find a bounded monotone subsequence you know that is going to converge. So we're going to use a two-pronged strategy to find a bounded monotone subsequence. We're first going to prove that every sequence, bounded or not, has a monotone subsequence. And then in the case where our sequence is bounded, then we're going to get a bounded monotone subsequence that will then be convergent. So let xn be any subsequence, and recall the following. So remember our old friend Sn, that is the set of all terms in the sequence starting at xn and then after as well. And then we had our an, which was the infimum of Sn. So let's look for a monotone subsequence using those concepts. So we're going to use kind of 2 strategies depending on which one works. Our first strategy is going to be the following. So recall an is an increasing sequence. It would really be nice if those ans could themselves be actual terms in the original sequence, not just terms in the an sequence. And that might happen if xn equals an. Now, this isn't going to happen all the time, and in fact, it may not happen very often at all. But it will happen if xn happens to be the smallest element in Sn. So then what we do is when that happens, we put xn in the subsequence, and if it doesn't happen, we just leave it out. Remember, we don't have to get every single term in the sequence to be in there. We just have to get enough to make a subsequence. So suppose we end up after this process with a subsequence, right? X sub pn, where each x sub pn is equal to a sub pn. Well, whenever m is less than n, we have pm less than pn, right? That's the definition of a subsequence. That means a sub pm is less than or equal to a sub pn. That's what it means for a sub n to be an increasing sequence. But remember, a sub pm is equal to x sub pm, a sub pn is equal to x sub pn, so that tells us that x sub pm is less than or equal to x sub pn, and that gives us an increasing subsequence. So if this strategy actually gives us an infinite subsequence, right, we get infinite many terms in there, this strategy will work to give us an increasing subsequence. But of course, you probably figured out the potential problem. What if we only get finitely many x sub pn such that x sub pn is equal to a sub pn? In that case, this strategy is not going to work. that means we have to go to strategy 2. So in strategy 2, we're going to say, okay, maybe some of the xn's have xn equals an. Let x sub big N be the last one for which that happens. And if we have only finitely many, there will be a last one, and after that, infinitely many where that never happens. So that means that if little n is bigger than big N, then xn will never be equal to a sub n. And then all we're saying there is that in those cases, xn cannot be the minimum value for Sn for any of the little n's bigger than big N. So here's where we go to our second strategy. We'll start with our first element in our first term in our subsequence is going to be x sub n plus 1. Now, we know that x sub n plus 1 is not equal to a sub p1, right? So that means x sub p1 is bigger than a sub p1. And remember, what we know about a sub p1 is it's the infimum of s sub p1. So any number bigger than it, in other words, x sub p1, is not going to be a lower bound for s sub p1. But what that means is there's some x sub p2 in s sub p1, right? In other words, p2, it has to be bigger than p1 in order for that to happen, where x sub p2 is less than x sub p1. And now you can sort of see that we're getting the beginning of what is hopefully going to be a decreasing subsequence. And then we just keep building this subsequence recursively. So each time we get a new term, we'll use that term to create hopefully a smaller term that is further out in the sequence. So given x sub pn, we know that x sub pn is not a lower bound for s sub pn, right? That's because we're way bigger than x sub big N right now. That means there's going to exist some x sub pn plus 1, where x sub pn plus 1 is in that s sub pn, but it is, right? That means pn plus 1 is bigger than pn, but that x sub pn plus 1 is smaller than x sub pn. And then that gives us our recursive definition of our subsequence. And you can see that every new term we add is going to be smaller than the previous term. So that gives us a decreasing subsequence. Actually, it gives us a strictly decreasing subsequence, if you really care about that. But we actually don't, because all we need is something that will converge when we get boundedness. So that gives us our theorem, let xn be a sequence. Then xn has a subsequence that is monotone. In the case that we use strategy 1, it gives us an increasing sequence. In the case that we use strategy 2, it gives us a decreasing sequence. So it could be either. So our proof, let xn be a sequence. For each little n natural number, define Sn as we defined before. We have two cases. Either xn is the minimum value of Sn for infinitely many n, or xn is the minimum value of Sn for only finitely many n. There's only two possibilities, those are them. In case 1, what are we going to have? We let xpn be the subsequence that consists of all the xpn's that are minimum values of Spn, and we claim that's an increasing sequence. So if m is less than n, we have pm is less than pn. Then we have x sub pn and s sub pm, because n is bigger than m, right? Since x sub pm is the minimum value of spm, we have x sub pm less than or equal to x sub pm, which makes it an increasing sequence. Yay! For case 2, xn is the minimum value of Sn for only finitely many n. Here, we're going to let big N be the largest integer such that xn is the minimum value of Sn, and we're going to define our subsequence recursively. Again, we gave the recursive definition before. X sub p1 is going to be x sub n plus 1. And every time we've defined x sub pn, we note that pn is bigger than n. That means x sub pn is not a lower bound for s sub pn, which means that we have some x sub pn plus 1, where pn plus 1 is bigger than pn, that is smaller than pn. And then it's clear this makes xpn a decreasing subsequence, which completes the proof. And as a corollary, we get the Bolzano-Weierstrauss theorem. Every bounded sequence has a convergent subsequence. The proof is pretty easy. Let S be a bounded sequence. Any upper or lower bound for S will be an upper or lower bound for every subsequence of S. And so every subsequence of S is bounded. By the previous theorem that we just proved, there exists a monotone subsequence of S. Since this subsequence is both bounded and monotone, it is convergent, which completes the proof. All right, so now I want to move into talking a little bit about our limit inferior and limit superior. If xn is any subsequence, remember our Sn. How can you forget? It's been following us for a while. An is equal to inf of Sn, and Bn is equal to the supremum of Sn. And actually, it's possible that our sequence is not bounded. So if Sn is not bounded below, we just formally say that An is equal to negative infinity. I know negative infinity isn't a proper number, but all we're indicating is that it's not bounded below, so we can't give An a number. And the negative infinity indicates that it's not bounded below. And similarly, if Sn is not bounded above, we say that Bn is equal to infinity. An is increasing, so it converges to some number A, or if it's not bounded above, we just say A equals infinity. And then Bn is decreasing, so it converges to some number B, but again, if it's not bounded below, we just say B is negative infinity. And with A and B defined as above, we call the limit inferior of xn, also written lim inf n goes to infinity of xn. That's what A is, and then B is the limit superior. And also written lim sup n goes to infinity of xn. So here's a theorem that we're going to be working on in the in-class activities. Let xn be a sequence, then xn converges if and only if the lim inf of xn and the lim sup of xn are finite and equal. And in that case, the sequence converges to the lim inf and the lim sup. Shouldn't be too much of a surprise because that's kind of what we proved when we were doing our Cauchy sequences, right? So, of course, our observation is we proved the Bolzano. One observation I want to make you aware of with regard to the Bolzano-Weierstrauss theorem is that it may have seemed kind of odd that we only used the ANs to prove the Bolzano-Weierstrauss, both when we had an increasing and a decreasing sequence. Kind of weird that the BNs weren't in there. But it turns out you can prove it using the BNs. And again, you kind of use a mirror strategy. It's going to sort of be a mirror image of what our proof was for the ANs. See if you can try it. It's a good challenge for you, I think. And if not, you can work on the in-class activities for the limit inferior and limit superior, where you're going to actually prove that theorem. That's at the link below this video.